Welcome to the deep dive. We are really thrilled you're joining us today for this one.
Oh, absolutely. It's a fascinating topic.
It really is. I mean, imagine a mathematical equation so massive, like so sprawling with interacting variables, that if you printed it out, it would stretch from New York to London.
Right, just an incomprehensible scale.
Exactly. And a human mathematician might spend their entire career staring at just, a single inch of that equation, relying on their brilliant but ultimately limited intuition to understand it.
Because that's all a human brain can hold at one time.
Yeah. But now imagine a machine ingesting that entire transatlantic string of logic, processing it in like an afternoon, and casually pointing out a hidden structural flaw that no human could ever step back far enough to see.
It's wild to think about. It's an AI that isn't just crunching numbers, it's seeing the invisible architecture of our universe.
Right. And our sources today put us right on the cutting edge of that transition. We're digging into an AI news digest from March 26th, 2026.
Which highlights some massive shifts.
It does. And the absolute centerpiece of this digest is a featured article from Technology Review. The headline really sets the stakes right away. It reads, "This startup wants to change how mathematicians do math."
Which, is a monumental ambition, right?
Right.
Mathematicians have been doing math the same fundamental way for millennia.
Yeah, you have a brain, you establish some logical rules, and you try to build a bridge from an unknown to a known, step by step.
Step by logical step. But the reality emerging now is that AI is stepping into the most abstract, specialized, and mysterious realms of human thought.
So the mission of our deep dive today is to explore how this new wave of artificial intelligence is fundamentally changing how we approach that bridge. We're going to look at the mechanics of how an AI actually reads math.
And why human cognition is hitting a physical limit.
Exactly. And how handing this tool to experts could unlock everything from next-generation physics to global economic models. So, okay, let's unpack this.
Well, to really understand the disruption here, we have to look at the specific catalyst.
Yeah.
The Technology Review article centers on a startup called Axiom Math.
Out of Palo Alto, right?
Yes, operating right out of Palo Alto. And what they've done is unveil a new artificial intelligence tool named Axplorer. That's Axplorer.
I do love the inventor's naming convention there.
It's very startup-esque, but the detail that jumps out immediately is that this tool is completely free.
Wait, really? Completely free?
Completely. They haven't locked it behind some institutional paywall or a massive enterprise license. They're distributing it openly to the mathematical community.
Which is huge for adoption. That guarantees, rapid widespread testing.
Exactly. But, Explorer didn't just materialize out of thin air. The source text details a very specific lineage.
Right. It evolved from something else.
Yeah, it's a reimagined version of an earlier system called Pattern Boost.
And the connective tissue between Pattern Boost and this new startup is a research scientist named Francois Charton. He co-developed that original tool, right?
He did. And then he brought that foundational architecture over to Axiom Math to help build Explorer.
So what was Pattern Boost actually doing? Because I feel like to understand Explorer under the hood, we need to know what the predecessor was up to.
It's a great question. Charton's earlier work was revolutionary because he and his team realized something very specific about the nature of mathematics. Equations have a syntax.
Like a grammar.
Exactly, a grammar. A complex formula is essentially a sequence of symbols, much like a sentence in English is a sequence of words.
So he treated advanced math like a language translation problem. That's fascinating.
He really did. Pattern Boost took massive databases of mathematical theorems and fed them into transformer models, the same underlying architecture that powers large language models.
Oh, wow. So the goal was to see if the AI could just learn the language of math.
Yes. Without being explicitly programmed with every single hard-coded rule of calculus or algebra, it was looking at math syntactically.
Okay, which brings us to the evolution into Explorer. If Pattern Boost was learning the grammar, Explorer seems to be reading the entire library and finding the thematic connections between the books.
That's a great way to put it.
Let me try an analogy here to help visualize this for you listening. Think about the difference between traditional math tools and Explorer, like the difference between a detective using a magnifying glass versus using an electron microscope.
I like that. The magnifying glass is great for the immediate clues.
Right. Historically, human mathematicians have been on their hands and knees with that magnifying glass, looking at a million-piece jigsaw puzzle scattered across a gymnasium floor.
They're brilliant at looking at the specific shapes of the pieces right in front of them. The curves, the flat edges,
And logically deducing which two adjacent pieces snap together.
which is that step-by-step logical deduction. Highly precise, but strictly localized.
But Explorer isn't on the floor looking at cardboard tabs. Explorer is hovering 50 feet above the gymnasium. It's looking at the entire floor at once.
Yes, the perspective shift is everything here.
And from up there, it notices, say, a subtle color gradient spanning 100,000 pieces that the person on the floor physically cannot perceive because they are just too close to the puzzle.
Exactly. The AI maps these equations into high-dimensional vector spaces. Where a human can visualize a graph in maybe 2 or 3 dimensions, Explorer maps mathematical properties across thousands of dimensions.
Thousands. That's just nuts.
It is. And in that space, distance equates to mathematical similarity. So, two equations that look completely unrelated to a human on the floor might be sitting right next to each other in the AI's high-dimensional space.
Okay, but applying that hovering over the puzzle concept to actual mathematical data, that's where my brain starts to hit a wall.
It's a lot to wrap your head around.
I mean, I have to push back on this premise on behalf of the listener because it feels counterintuitive to how we're taught math. Math is pure logic, right? 1 + 1 is 2.
Sure, absolutely.
So if there's a structural pattern in an equation, how can it go entirely unnoticed by the smartest human minds for generations? We have geniuses devoting their lives to this. Are we claiming this software is just inherently smarter than Einstein?
What's fascinating here is that the answer requires us to separate intelligence from capacity. It's not about the AI possessing some superior spark of genius.
Okay, then what is it?
It's about the severe biological limits of human working memory when faced with unimaginable scale.
The biological limit, like our brains can only hold so many variables at once.
Exactly. Human cognition relies on abstraction and intuition. We're incredible at conceptual leaps. But when a proof involves tens of thousands of interacting variables,
Or stretches across thousands of pages.
right, a human simply cannot hold the entire structure in their minds simultaneously. To engage with it at all, a human has to simplify it. They use heuristics, they look for elegant pathways, they zoom in on a manageable slice.
Because if we don't zoom in, we're paralyzed by the noise. But by zooming in, we lose the macroscopic view.
Precisely. The AI doesn't have a working memory limit. It doesn't need to simplify the equation. It ingests the ocean of data simultaneously. It never gets fatigued.
It never loses the thread of a 10,000-step logical sequence.
Right. So when Explorer highlights a hidden pattern, it isn't experiencing Einstein-level inspiration. It's simply able to observe the entire massive architecture at once.
It identifies a structural regularity that is mathematically invisible if you only look at the localized pieces. Okay, let's anchor this in something concrete, though. Abstract math can sound a bit dry.
Fair enough.
What does a problem like this actually look like in practice?
Well, consider knot theory. It's a field of topology that studies mathematical knots. To a human, classifying these knots involves looking at crossing numbers, how many times the loop crosses over itself.
Okay, makes sense.
But when knots get incredibly complex, humans get lost in the sheer volume of crossings. But an AI mapping that same knot into a high-dimensional vector space might instantly spot a topological invariant.
What's a topological invariant?
It's a fundamental property of the knot that doesn't change no matter how you twist it. The AI sees it instantly because it's looking at the structural geometry in a way human visualization just can't accommodate.
Wow. So the pattern was always there, encoded in the absolute logic of the math, but it was stretched out across a canvas far too massive for our biology to process.
Exactly.
We've effectively been trying to read a sprawling novel through a microscope, and Explorer just removed the lens and let us see the whole page.
And stepping back to see the whole page shifts the entire paradigm of mathematical research. The digest text makes a very specific, aggressive assertion here.
Which is?
It states that this tool doesn't merely accelerate the pace of current discovery. It actually expands the very boundaries of what we consider solvable.
Expanding the boundary. So moving problems from the impossible column to the possible column.
Yes, and that leap from theoretical mathematics into the physical world is where this stops being an academic curiosity and becomes the global catalyst.
That's the ripple effect. And the text explicitly names the disciplines that stand to be most heavily influenced here. It mentions physics, engineering, and economics.
Those fields are heavily emphasized because they are structurally reliant on the math we're discussing.
Right, theoretical math isn't just an isolated discipline.
No, not at all. It's the underlying operating system for the physical sciences. All of these fields rely on complex mathematical models as their foundation.
It's like a keystone. Cracking one abstract mathematical conundrum could act as the keystone that suddenly unlocks a highly complex economic model or clears a massive engineering bottleneck.
Let's look at engineering as an example. If an aerospace company wants to design a new hypersonic jet,
Or a lab wants to create a room temperature superconductor.
right, the physical construction isn't their first bottleneck. The bottleneck is the math. They're dealing with fluid dynamics or quantum mechanics at a level of complexity that defies straightforward calculation.
So what do?
They encounter equations like the Navier-Stokes equations for fluid flow, which are notoriously difficult to solve in turbulent conditions. Because the pure math is too tangled, engineers are forced to use approximations.
They build heuristic models, educated guesses.
Exactly, they guess to bridge the gap.
But every time you use an approximation instead of a pure mathematical truth, you introduce inefficiency, right? Like you have to build the jet wing a little heavier just to be safe.
Or run a fusion reactor a little cooler because you aren't perfectly sure how the plasma will behave. The approximations are basically a tax on innovation.
A tax on innovation. I like that.
Yeah.
But if an AI like Explorer can sift through the underlying mathematical structures and find the exact hidden pathway to solve that fluid dynamic equation,
The tax vanishes.
the bottleneck breaks. You replace the approximation with an absolute mathematical truth. Suddenly, the engineer can design the wing perfectly.
And the economist trying to model global supply chain disruptions involving millions of distinct interacting agents finally has an equation that can hold all those variables without collapsing.
When the math levels up, the whole discipline levels up.
Yeah.
By feeding these applied fields fresh AI-driven discoveries, we're injecting them with entirely new foundational algorithms.
Which alters everything from the efficiency of the power grid to the stability of financial markets.
So the bridges you drive over, the systems your retirement accounts rely on, the energy powering or all of it could fundamentally shift because a tool in Palo Alto found a hidden connection in a sea of data.
It's a perfect microcosm for a much larger global shift happening across the workforce.
Right, and if you're listening to this right now thinking, well, I don't work in quantum topology or macroeconomics, so this is just science fiction, we really need to zoom out to that macro trend.
Because the Technology Review article situates Axiom Math's work within a much wider movement. This isn't isolated to mathematicians staring at chalkboards.
It's a vanguard example of AI being increasingly integrated into highly specialized fields. Though, the immediate cultural reflex when we hear about AI entering specialized knowledge work is anxiety.
Oh, of course. The fear of automation.
The fear that the algorithm is arriving to replace the expert.
But the source material explicitly rejects that framing. It makes a crucial distinction. This is not a story about the automation of mathematicians.
What is it then?
It's a testament to the versatility of AI to transcend traditional boundaries. It redefines what human collaboration with technology can achieve. The AI isn't functioning as a replacement, it's functioning as a co-researcher.
That distinction is so critical. A replacement does the work and hands you the final product. A co-researcher sits beside you, processes the data you physically can't, and presents an anomaly for you to interpret.
The AI brings the unfathomable scale. The human brings the intuition, the context, and the understanding of why that anomaly matters in the physical world.
Because Explorer can't build the hypersonic jet. It doesn't know what a jet is.
Exactly. It only knows the vector space. It requires the human engineer to take that pattern and translate it into a physical wing. It actually forces the human expert to ask better, more ambitious questions.
Because the AI removes the friction of the calculation, which means that whether you work in logistics, healthcare, legal research, this macro trend means you might soon experience your own Explorer moment.
It's highly likely.
Imagine sitting at your desk, and instead of wrestling with a database to pull a standard report, you're conversing with an AI co-pilot that says, I just reviewed every piece of supply chain data from the last decade, and I found a structural inefficiency hiding in the noise.
It fundamentally changes the day-to-day reality of the knowledge worker. You transition from being a data cruncher to an insight director.
You're steering the ship while the AI navigates the incredibly dense currents beneath the surface. It elevates the human role by offloading the brute force processing. We move from using tools to partnering with them.
Which is a beautiful way to frame it.
And that really brings us full circle on the journey we've taken today. We started with the arrival of Axplorer from Axiom Math in Palo Alto.
We examined its lineage, evolving from Francois Charton's work, treating mathematical syntax like language in Pattern Boost.
Right, mapping equations in high-dimensional space. And we dug into the mechanism itself, how the AI bypasses the biological limits of human working memory.
Hovering above the puzzle, seeing the gradients we literally cannot perceive.
And we traced those massive real-world ripple effects, how solving abstract problems removes the reliance on approximations in physics, engineering, and economics.
All of which points toward a profound paradigm shift in problem solving.
It does. But as we wrap up this deep dive, I want to leave you, the listener, with a final thought to mull over. Something that builds on this collaborative dynamic but pushes it one step further.
Oh, the philosophical implications are always the best part.
They are. Think about the core premise we just established. AI is discovering mathematical truths by perceiving patterns across dimensions our brains simply cannot hold. The logic is just too vast for human working memory.
Right.
So as these AI tools become even more advanced and integrate into other fields, will we eventually reach a point where we have to accept answers to the most complex, high-stakes problems without actually being capable of understanding the logic behind them?
That is a chilling thought. We're moving from a scientific culture that demands you show your work.
To a reality where we might simply have to trust the pattern. If the math is too sprawling for a human brain to verify, do we surrender the need to comprehend the journey, as long as the machine delivers the correct destination?
It's a staggering question about the future of human knowledge.
It really is, and it's something to definitely keep in mind as we watch this all unfold. Thank you so much for joining us on this deep dive.
It's been a pleasure. Stay curious out there.
Keep questioning, keep exploring, and we will catch you on the next deep dive.